Okay, so let's take a look at this one. We're given just the KSP, so it definitely should be an ice table situation here. We are also given the KSP, so we know this guy's going to be really a solid. It will break apart into an aluminum and 3 hydroxides here. Our KSP expression here will be our aluminum times our hydroxide. Again, we do need to cube it because of the coefficient that we see there as well. We're going to do an ice table here. Going to be 0 and 0. Change going to be plus S. And again, we want to make sure that we do take the coefficient into account here in addition to up here where we have it in our KSP expression. At equilibrium, we're going to have an S and a 3S in this case. Any questions so far? Going into our expression there, that's going to give us S times 3S cubed. And once again, you do need to do both of those things. We will equal our KSP that was given to us 2 times 10 to the minus 32. That is going to give us something like a 27S to the 4th is 2 times 10 to the minus 32. Don't forget that you're not just squaring the S, but you also need to, are cubing the S. You need to also cube the 3, which I can't tell you how many times people forget to actually cube the 3 part of it. So make sure that you do the number and the letter that you got going on there. Bless you. And that's, again, how we get to our 27 that we see here. We need to divide the 27 to the other side, and that will give us S to the 4th is equal to 2 to the minus 32 divided by 27. 7.407 times 10 to the minus 34. We need to take the 4th root there on both sides. And if you do that, that's going to get you something. 1 divided by 4. We'll get you. Okay. 5.2 times 10 to the minus 9 molar, which would be our molar solubility. By the way, to take the 4th root here on your calculator, you could do caret parentheses 1 divided by 4. That's the 4th root. If you don't have a root button there, 1 divided by 2 would be a square root, 1 divided by 3 would be the cube root, and so forth. If you don't have one of those buttons like that, that's how you could put it. Caret parentheses 1 divided by whatever root you want to do. You might end up on your calculator with a bunch of zeros and a 5 at the end if you ran out of room. If you put in scientific notation, which everybody would do, and you would get that 5.2 times 10 to the minus 9 there. That would be, in this case, the concentration of our aluminum, right? As that is equal to X, or S, which is 5.2 times 10 to the minus 9. If I wanted the concentration of hydroxide, though, what should I have to do? I would have to multiply it by 3 because that does equal 3S there. That means that we would have 3 times our 5.2 times 10 to the minus 9. And that would give us something like 1.6 times 10 to the minus 8 would be our concentration of hydroxide. So that is the molar solubility in this case of aluminum hydroxide. Is also, in this case, the concentration of the aluminum ions that are floating around in that solution. But we do have to adjust it by multiplying by 3 to get the actual concentration of the hydroxide ions that are floating around. Yeah. Yeah. So basically, aluminum hydroxide will definitely be a solid because there's a KSP value associated with it, which means that it's something that's insoluble. Saturated solution means that you basically have added enough to pretty much things are not going to dissolve anymore. So you put in there the maximum amount of that, say, aluminum hydroxide that would dissolve at that particular temperature. So it's right at that point where if you keep kind of putting it in there, no more will dissolve. And that's where we kind of tip from a saturated solution to a supersaturated solution. So that concentration is pretty much the concentration of aluminum hydroxide that you could get to dissolve in that solution before you start to see the solids. And that would be the concentration at that point of the aluminum that's floating around in there. And 3 times that number would be the concentration of the hydroxide that's freely floating at that point of it. But saturated solution means basically that you pretty much dissolved as much solid as you could get in there. And usually, you have like a little bit of solid kind of left over at that point because no more will dissolve. Other questions? But again, this is what we're talking about also as well. Maybe if you're not sure about your solubility rules or something like that, if you see a KSP value associated with something, then it's pretty safe bet to assume that it's a solid. And that's where it's going to start with. Otherwise, it pretty much won't have a sort of a KSP sort of value associated with it. Other questions? Okay. All right, so can we use KSP values to help us decide what thing will be more soluble or not? The answer is yes and no. So it depends on the situation as to whether or not you can sort of use the KSP values directly to determine, which one is more soluble, which one you would actually expect to precipitate out first in a solution. So if we look at something like silver iodide, when it breaks apart, it's going to break apart into a silver ion and an iodide ion here. We take a little copper 1 iodide. That's going to break apart into a copper 1 solution, copper 1 ion, and an iodide. And if we look at calcium sulfate in this case, going to break apart into a calcium ion and a sulfate ion in this case here. Now, when we look at the KSP values for all these, we can actually use them to directly compare each of these to see which one would be more soluble versus the other. And the reason we could do that is what we actually see on this side of the arrow. We see the same number of ions. So this guy has 2 ions it forms, this guy has 2 ions, and this guy has 2 ions that it forms. And if you're comparing 2 things that form the same number of ions, you could use the KSP value to determine solubility. And because the KSP value is the same thing as a K value, that means if we have a large value of K, we should mainly have reactants or products. We should mainly have products. And in the case of KSP, we always have solids on the left and aqueous ions on the right, which means the larger the KSP value, the more products we would have, the more aqueous ions we would have, which means that it is actually dissolving, right? So it's not staying together. So it actually would be more soluble in that case. Opposite is true if you had a smaller KSP value. That would mean you would have more reactants at equilibrium, and more reactants at equilibrium would mean that you have more solid, which means it would be more insoluble. So in this case, if we did compare the KSP values of these 3 guys, we would see the calcium sulfate has the largest KSP value, which means out of those 3, it would be the most soluble. And silver iodide has the smallest KSP value, which means out of those 3, it would be the least soluble. Question on that. So it's really important when we're, good. I take your retraction and I will continue on. Then we're so formal here. Did I give you some candy? You're all formal. All right. So we could only again compare the KSP values based on if you're comparing 2 things, kind of like apples to apples. So you got the same number of ions. If you do not have the same number of ions actually being formed, you cannot directly use the KSP values to do that because the math is different. The math in each of these cases is going to end up being S squared equals the KSP value. Right, if you did your ICE table for each of these, since there's S and S on each of these, that means as a direct comparison, you could compare high and low based off of that. But when you look at something, for example, like these 3 salts here, when we look at copper 2 sulfate, when that breaks apart into ions, we will get a copper 2 ion and a sulfide ion there. And that's 2 ions, obviously. If we take a little silver sulfide, that's going to break apart into 2 silver ions and 1 sulfide ion. And that's a grand total of 3 ions in that case. And obviously here, if we take our Bi to S3, we're going to get a bunch of ions here, but 2 of the Bis and 3 of the sulfides in this case. I'm going to go on a limb here and go with 5 in this case as the number of ions and particles that we got floating around there. So if we were to look at the KSP values that we could get from a table here, we see that the copper 2 sulfide is to the minus 45. Our Bi2S3 is actually to the minus 73. And our silver guy is in the middle. If we went solely based on KSP values, this would be the largest, which we would expect this guy to be the most soluble. But it actually is not. If you do the calculation, it is actually the opposite way, and this guy would be the least. This guy on the bottom is actually the most soluble, and this guy is actually the least. So when we're comparing things that make more than our different numbers of ions, we cannot use the KSP value directly to compare them. In terms of solubility, we actually have to do the calculation like we were doing just previously in some of those examples. So you have to do the ice table and actually do the calculation to figure out what the solubility is. As you see here, it is definitely different than what you would expect based on the KSP value. So to a limited degree, you can use a KSP value to compare things that break apart into the same number of ions, but if they do not, you do have to actually do the calculation for everybody to figure out which one is more soluble and which one is least soluble. Any questions on that there? All right, then let's talk about, first off, some things that affect solubility. And one of the things that affects solubility is the common ion effect, which is what we talked about when we talked obviously about buffers in our favorite chapter ever, which is chapter 14. Here, the presence of a common ion will actually decrease the solubility of the salt. So if you just think logically about how these guys are written in terms of their equation, you have solid, as we've talked about, going to aqueous ions, which means the only place that you could have a common ion would be on the reactant side or product side. It would be on the product side, which means if you do have a common ion, that would be like adding a product, which means Le Chatelier's principle is going to cause the equilibrium to shift away, and that is going to make more solid. So much like how a common ion keeps a weak acid and weak base together, instead of allowing it to break apart, the presence of a common ion here with our KSP will do a similar sort of situation. It will actually keep that solid together. So we could actually see the effect of it in these two examples here. If we look at silver bromide, this is the KSP for silver bromide. And if we look at it in water, what's going to happen is our silver bromide will break apart into a silver ion and a bromide ion. And initially we have 0 and 0. Our change will be plus S and plus S. As the coefficients are 1 there, we will end up with S and S. This will go into our KSP expression, which would be the silver ion times the bromide ion. And that's going to give us basically S squared is equal to 7.7 times 10 to the minus 13. We're going to do a little square root action on both sides there. And that's going to give us a molar solubility here of 8.8 times 10 to the minus 7 molar for our silver bromide. So the solubility of silver bromide is 8.8 times 10 to the minus 7 molar. Again, just a reference point in terms of what that means. We use the molar mass of silver bromide, which I think is 107.9 for the silver, a little 79.90 there for the bromine. Going to give us like 187.8 grams per mole. It's going to give us a solubility of like 1.7 times 10 to the minus 4 grams per liter. So basically we could dissolve in this case 0.0001 0.17 grams in 1,000 milliliters of water, basically. Also, much like the silver chloride we saw, not very soluble, right? Which is why we consider this to be insoluble. So what happens if we actually have this guy in a solution that contains sodium bromide? So what will change here? So the sodium bromide is a strong electrolyte, which means when it goes for a swim, it will break apart into sodium ions and bromide ions. And in this case here, if we set up our equilibrium, which is going to be our silver bromide, which is the only thing that will set up an equilibrium, our ice table will look slightly different. We will initially have none of the silver, but in this case, do I have any of the Br minus? Yeah. I do, and it's coming from the sodium bromide. So since this guy is 0.001, it is a 1-to-1 relationship between that and the bromide, which means the bromide would be also that same concentration. So we actually would have a concentration here supplied by the sodium bromide, giving us an initial Br minus concentration. At this point, the rest of the ice table is going to be very similar, plus S, and that means that at equilibrium here, we will have S and 0.001 plus S. Any questions on that there? We can now go into our KSP expression like we did previously. Let's clear out some of this maybe here. And if we do that, what that's going to give us is S times 0.0010 plus S equals 7.7 times 10 to the minus 13. That is a large value of K, small value. It's a small value of K, which, as we know, means we're not going to have a tremendous amount of change, which means we can assume S is equal to 0 in this case, which why not? It will make it easier, I hope. That means that will give us S times 0.001 is equal to 7.7 times 10 to the minus 13. That's going to give us an S here of 7.7 to the minus 13 divided by 0.001. Going to give us 7.7 times 10 to the minus 10 molar of our silver bromide as the molar solubility, which if we multiply it by the molar mass of 187.8 grams per mole, will give us 187.8. 1.4 to the minus 7 grams per liter, right? So we could compare either one. We could compare the molarity here between it and water and it with the common ion. Which one has the higher solubility? The one in water or the one with the common ion? The one in the water, which is this one, is a larger number. So it is more soluble in water in this case, because with the presence of that common ion, it's going to cause this equilibrium to shift to the left and keep it together, meaning that it's going to be less soluble and less of it will break apart. So the presence of a common ion is one factor that can affect solubility, and the presence of that common ion, much like what we saw with buffers, will kind of keep everybody together because it's going to force it back to the left in this particular case. The additional step here is you do have to have an initial concentration. By the way, I didn't write it, but you can check your answer there of 7.7 times 10 to the minus 10 and divided by 0.001, and you're nowhere near 5%. So your assumption is good. You should probably check it, but I would say probably in most cases, I won't say all the cases, but in most cases, you'll probably be okay on most of these, but you should still kind of give it a little check and see if it's okay as well. Any questions on common ion and how it affects it? Yeah. I would so we would want to compare apples to apples, so either one. So I would compare this concentration, which is what the molar solubility of it is with the common ion, to what the molar solubility of it is in water. So these two numbers. And really at that point, you could just compare the -7 to the -10. A reminder again, as we might have talked about again, the smaller negative exponent, right, is the larger number because less zeros in front. You could also compare this number, which is in grams per liter, to this number. And again, that -4 is much larger than the -7 would be. But you definitely don't want to compare one to the other. So you definitely got to compare the same units. Other questions? Okay. So this is one factor that can affect solubility. Let's talk about another factor that can affect solubility. After we do this example, we'll talk about that. So why don't you try that? I don't know. It's going to cancel the rest of the day, I think. I don't know. It's almost like I'm not here anyway. So all right, try this one. Why pull myself up here? I might need more chocolate. I don't know. Let's see. Okay, let's take a look. So once again, we're given the KSP. So we're going to start with our equation here. Little silver chromate. Going to break apart into a couple silver ions and a chromate that looks something like that, perhaps. Our KSP here would be our silver concentration. Once again, we do need to square it because of the 2 times our chromate there. And that's going to equal our 9 times 10 to the -12. Here it is in a solution of potassium chromate, which is K2CrO4. That is going to break apart as potassium is soluble in everything into a couple of potassiums and a chromate. In this case, it is the chromate here. That's our common ion that we have. And it is going to be 0.1 molar, as it is a 1-to-1 relationship between those two. So that's important here, kind of like the buffer. If you don't put this here, you're not doing obviously the common ion part of the problem, which is kind of the important part of it. So you got to make sure you got that guy on the right hand side. The change here going to be plus 2s, again because of the coefficient there, and plus s, and that means that at equilibrium we have 2s 0.1 plus s. Remember, that is a plus on that side, not subtracting. We're going to take this into our KSP, which will give us 2s squared times 0.1 plus s is equal to 9 times 10 to the -12. Any questions so far? At this point, we can once again make an assumption, as that K value is obviously really small. So we're going to assume that S is equal to 0 here. Once again, we can't get rid of all the S's, or we have nothing to solve for. That's going to give us 4s squared times 0.1 is equal to 9 times 10 to the -12. You could do whatever you like here, to divide them separately or multiply them and then divide. So we'll take 9 to the -12 divided by 0.1 and divided by 4. Going to give us s squared is equal to 2.25 times 10 to the -11 in this case. Any questions so far? At this point, we're going to square root both sides. So do a little square root action there on both sides. And if we do that, square root, going to give us 4.7 times 10 to a lot of zeros. 1, 2, 3, 4, 5, 6, maybe as well. We could also divide this by 0.1, times it by 100, and our check is good here when you do that. That in this case would be the molar solubility of this particular compound, as that is going to be basically what this guy will be at this point. And that's in moles per liter. Obviously, if we wanted grams per liter, we use the molar mass to convert it. If I wanted the silver's concentration, though, I need to take that number and multiply it by 2, right? And if I really want what chromate's concentration is at that point, it would be 0.1 plus that. The majority of that 0.1 is going to come from the common ion, right? That's why it's so high, right? Because we dumped in basically 0.1 molar. As you can see, it's not going to change very much from that. We're not going to produce a lot of free chromate besides the 0.1 that we dumped in there. Any questions on any of those things there? Yeah. You could do either one, yeah. So technically, if it doesn't specify, usually they'll be pretty good about specifying, given it in molar solubility or grams per liter. But really, if they don't, you technically give it in any sort of solubility unit you want. Yeah. Other questions? All right. Dare I say that is common ion. Let's take a look at the next thing that could affect solubility. Maybe. There it is. There's pH. So let's take a look at pH and solubility and what happens when we are playing with the pH. The presence of a common ion, as we just saw, will decrease the solubility because it's going to push it back the other way and keep it together. When we play with the pH, what will happen is if you have an insoluble base, it will dissolve in acidic solutions. And if you have an insoluble acid, it will dissolve in basic solutions. So let's take a look at magnesium hydroxide, which I'm going to guess is a base since there's hydroxide happening there. So let's take a look at this guy. And the KSP for magnesium hydroxide there is given, which is 1.2 times 10 to the minus 11. We're going to run through our ice table here and see what we get. So actually is move my KSP up here. KSP 1.2 times 10 to the minus 11. All right. So if we ran through our ice table, we would go 0 and 0. We would do our plus S and plus 2S. And at equilibrium, we would have S and 2S. Our KSP expression at this point would be the concentration of magnesium times the concentration of hydroxide. And once again, here we do need to square it because of the coefficient that we see there. Putting our values into there, that's going to give us basically KSP will equal S times 2S squared, and that will equal our 1.2 times 10 to the minus 11. Doing a little combo action there, that's a 4S cubed. Remember, we got to square the 2 as well, is equal to 1.2 times 10 to the minus 11. I'm going to divide it by 4. And that's going to give us 1.2 to the minus 11 divided by 4. There we go. That's going to be S cubed is equal to 3 times 10 to the minus 12. Going to do a little cube root action there. Yeah. Going to get us, and once again, you can do a caret parentheses, bless you, 1 divided by 3 if you don't have that button available to you. So if you do that, that is going to get us a S value in this case of 1.4 times 10 to the minus 4. First off, any question on that calculation? So very similar to what we did previously. Now, since we're talking about pH in this case, the one thing in this equilibrium that will help us get to pH is which thing? What thing will help us get to pH? The OH minus, right? So because I know at equilibrium, the OH minus concentration will actually be 2 times S, I could use my S value here, and I could find the concentration of hydroxide, which would be 2 times S. So that's 2 times 1.4 times 10 to the minus 4. And that will get me my 1.4 to the minus 4 times 2. Going to give me my 2.8 times 10 to the minus 4 molar. From that concentration, I could get the POH, which will equal minus the log of 2.8 times 10 to the minus 4. And if I do that, that is a POH of 3.55. And my pH then would be 14 minus 3.55. And that's going to give me a 1045, perhaps. as the pH. Any questions on what I just did? What I just did is find out what the theoretical pH of this solution would be, right? So if you had this solution sitting there, this solution should have a pH of 10.45, which is basic, which is what we expect it to be since it's hydroxide, right? So that's good. So what does that mean? So that 10.45 is basically our baseline pH for the solution. So what would happen if I decided to lower the pH less than 10.45? Don't even have to get it into acidic conditions. If I actually lower it even a little bit lower than that, what will happen here to my solubility? So if I wanted to lower the pH, what do I have to add to probably do that? Yeah, I have to probably add an acid, right? So I probably have to add an acid to lower the pH. And when we add an acid like HCl, which is a strong acid, we're basically adding more H plus to that solution, right? So we got basically floating around in there some magnesium hydroxide, some magnesium, and some OH minus. So if I decided to add an acid to this, I'm going to dump in my acid, whatever it may be. It's going to dump into the solution some H plus. What happens when the H plus goes into that solution with, say, the hydroxide? What is it going to make? It is going to come together here to make water. That means when we look at our initial reaction here, and our good friend Le Chatelier's principle, I am essentially doing what with the hydroxide? I am essentially removing this hydroxide as it makes water with the acid that I'm adding, which means the equilibrium should shift which way? Should shift to the right towards where I'm removing it. That means that the solubility of this guy would increase or decrease? It would increase because it's now going to be making more products, right? And on the product side is more ions, which means it's more aqueous, less solid. So that's what it means above when it says insoluble bases will be soluble in acidic solutions. And again, you don't even actually have to get it to an actual acidic pH. You just need to take it lower than its baseline 10.45 in this example to get it to start to dissolve. Any questions on that there? So what happens in the opposite case is if we were to take the pH above our 10.45 in this case, in order to take the pH above 10.45, we most likely are going to be adding a base, which is essentially adding some hydroxide, right, in this case. And again, if we could look at our reaction here in this situation, we are essentially adding more hydroxide, which means based on Le Chatelier's principle, it should shift to the left in this case, which means solubility should start to decrease, yeah, because you're going to be making more and more solid. So what's going to happen in this case is, again, we have sort of our solution, and instead of the hydroxide making something, you're just adding more hydroxide basically, right? So that's going to cause that equilibrium to shift to the left there in this case and make more solid. So it's going to become less soluble in this case. And obviously it was more soluble over here on our left-hand side, right? So that's the same idea. If you wanted more solid, you could increase the pH in this case. And by adding more OH minus, you will basically force that equilibrium back to the left there, and it will become more insoluble. Just like if you wanted to dissolve, you should add some acid, and it will force that equilibrium to the right and making it more and more soluble what you have in there. So pH plays a really big effect on the solubility of salts, especially salts that contain hydroxide. Maybe it contains some H plus as well, like an acid. it can really affect whether or not you actually see the solid form or not. There's a bunch of experiments that you used to do in this class, which is known as qualitative analysis. You should be really happy you don't do it anymore because they smell a lot. But the whole basis of it used to be the only labs they would do in this section of this class was all those labs, not here, but in a lot of places. But the idea of that sort of experiments is basically based on this. You kind of selectively precipitate out things. And a lot of the procedures when you do that sometimes confuse students when they read it. It's like make your solution acidic, then make it basic, then make it back to acidic. And you're like, why am I doing that in like 3 steps in a row? And the reason a lot of times you would do an experiment like that is for this reason here. By playing with the pH, what you're able to do is keep certain ions that you want still in the solution and allow other ones to precipitate out because the pH is right for that to happen. So the pH plays a really big role in whether or not, things would precipitate out or not. And something like this, where you could actually calculate the sort of baseline pH of that solution, you could use that as sort of your barometer as, okay, did I just take the pH above it or below it? And, what will happen in terms of the solubility of it. Any questions on pH and solubility? All right, let's take a look here. I think that's what we said. Yeah. All right, so will a precipitate form? As we talked about earlier, we can look at the Q value versus the KSP value to compare that. And once again, if you do have a Q value that's larger than the KSP value, then you would expect a precipitate to form. And if you have a Q value that's less than the KSP value, you would not expect a precipitate to form, and it would be soluble. This is really the third thing that can affect solubility. So far we've seen common ion can have an effect on solubility. pH obviously can have an effect on solubility, but the actual concentration of the ions can also have an effect on the solubility as they're floating around. Will they come together? And that also, speaking of that type of experiments, a very common thing that would happen in those experiments, you add a lot of reagents. And by the way, every time we add a reagent, for example, to a test tube, we're essentially doing what to that test tube? How do we calculate concentrations when we mix things together? We use what equation? M1 V1 equals M2 V2. We're basically diluting. So every time you add a reagent to something, you're basically diluting it, right? And that's really important in experiments like I was talking about, the qualitative analysis type experiments, because as you continue to add your reagents to do your experiment, you're lowering some of these ions concentrations to a point where under normal conditions, they would precipitate out, but maybe their concentrations are too low to actually precipitate out. So even though solubility rules may say that if you throw these two ions together, you should get a solid, the concentration is really a big aspect as to whether or not you will actually see the solid form. And if they're too sort of diluted, you may actually not see the solid form, even though solubility rules tell you you should. So for example here, if we take a look at this combination here of sodium hydroxide, and we're going to put it together with some calcium chloride. So the first thing that we want to know is whether or not, a precipitate will form. So we want to think about what we're going to get when we mix these guys together. So when we throw in our sodium hydroxide into here, that's going to basically produce two ions, right? A sodium ion and a hydroxide ion. When we throw our calcium chloride in there with it, that is going to produce a calcium ion and some chloride ions, right? So the goal here is to figure out, based on solubility rules, will we expect anything to sort of develop? We already know that sodium and chloride, soluble or insoluble? It is soluble. It has sodium, right? So that's soluble in everything. So I'm going to say that's going to leave us our calcium and hydroxide as really the only other option that could come together in this double displacement reaction, right? So calcium hydroxide could form, and that's the only thing that could form in this case. And we know it also will make a solid because we can find a KSP value for it, which is right here, which is 8 times 10 to the -6. So what you should do now is calculate Q for this and see if Q is greater than or less than the KSP that's given based on these conditions. So you're mixing 2 milliliters of sodium hydroxide at a molarity of 0.2 with 1 liter of 0.1 molar calcium chloride. So why don't you calculate Q and see what you come up with, and will you expect a precipitate in this case? So we do want to calculate Q, and it is calculated the same way as KSP would be calculated. Calcium hydroxide, again, here would break apart into a calcium ion and 2 hydroxide ions in this case. That means that Q would equal our calcium concentration, our hydroxide concentration, and again, we would need to square it because of the coefficient that's there. We actually need the concentration of each of these ions as they are mixed. So I'm going to convert my volume into the same unit. So 1 liter is 1,000 milliliters. So I'm just going to kind of convert everybody to milliliters. That's a little dilution, as we were just talking about action for each of these guys, right? So for the hydroxide, which comes from sodium hydroxide, as that's the only source of hydroxide, we would have our M2 would be our M1, which is 0.2 molar. Our V1 is 2 milliliters, and our V2 is the total volume, which is 1,000 milliliters plus 2 milliliters, right? So that's 1,002 milliliters in this case, which means 1,002 milliliters. Obviously, if you did in liters, you got like 1.002. That's going to give us 0.2 times 2 divided by our total volume. And that's going to give us basically 3.99 times 10 to the minus 4 molar. We'll do the same thing for our calcium. The only source of calcium is going to come from our calcium chloride. Its concentration there is 0.1, which would be M1. We're going to use 1,000 milliliters of it. And our total volume, once again, is 1,002 milliliters in this case. Going to give us 0.1 times 1,000 divided by 1,002. Going to give us 9.98 times 10 to the minus 2 molar. Any questions on those calculations there? Now that we have the concentration of each of these ions when they're mixed together, we could go into our Q, and our Q in this case would then be 9.98 times 10 to the minus 2 times our 3.99 times 10 to the minus 4. Once again, we still got to square it there on the back end. That's going to give us 3.99 to the minus 4 squared times 9.98 to the minus 2. Going to give us something like 1.6 times 10 to the minus 8, which is our Q value. We would then take our Q value and compare it to our KSP value. And in this case, the Q is less than, as minus 8 is less than minus 6. That means, would we expect a precipitate or no precipitate? No precipitate. Again, you could go opposite of where it's pointing, which means it would go to the product side, and all these guys on the product side is aqueous ions, right? So we would have no precipitate in this case. So even though solubility rules tells us that we should get a precipitate because of the concentration of the ions that are floating around, we actually won't see the precipitate in this case. So that's what I was talking about earlier. Just because solubility rules say it so, there's a lot of factors, as we just seen: concentration, pH, common ion, that could play a big role in terms of whether or not you actually see that solid form or not. Any questions on that? Oh, good.
I'm like perplexed. I understand what you did,
Thank you.
but like it's taking me some time to get this concept.
Okay. Okay. Other questions? No. Okay. It's big words today. I tell you, it's like. So let's continue with the perplexingness here. Let's say, so let's talk a little about a really sort of practical application of KSP and solubility. And that is pretty much like that experiment I was talking about. In those experiments, we oftentimes do what is sometimes referred to as selective precipitation. And selective precipitation is a situation where you got a bunch of ions that are flying around, floating around in the solution. Maybe they're flying, I don't know. But they're floating around in the solution, and you really only perhaps want to take out one ion at a time. And then you want to take out maybe the next ion, and that's again the idea behind sort of selective precipitation. So in this particular example here, we have a solution that has a bunch of bromide ions floating around, a bunch of chloride ions floating around, and basically we want to add some silver to it. And when we do add silver to this, we are going to get two solids that could form. We could get silver bromide that will form. We could also get silver chloride that will form. The problem is if we just drop in some silver, we will get them both to precipitate out. You can get basically solids to come out. And the problem though with it is they're both white solid, which means you would really have no way to go. I think this like white precipitate is the chloride. This one I think is the bromide. There will really be no way to really distinguish between the different precipitates that come out all at once because they both basically look the same. As you can see in this picture, for the most part in a solution, you wouldn't be able to sort of determine perhaps which one is which, and they'll all be mixed together. So we would want to maybe sort of selectively take one out and then take the next one out. So in this problem, we want to precipitate out only the silver bromide first, and then afterwards we could take out the chloride, but we want to really leave the chloride in solution. So we want to know how can we add the silver that it will only pretty much react with the bromide to make a solid, and leave the chloride still sort of floating freely in the solution. So we could actually use the KSP expression to help us with that. If we were to write the KSP here for our silver bromide, the silver times the bromide equals 7.7 times 10 to the minus 13. Now, what we do know is that the concentration of each of those ions, the chloride ion and the bromide ion, are 0.02 molar. Right? So if I rearrange the KSP expression and actually solve for the silver concentration, that would be our 7.7 times 10 to the minus 13 divided by the bromide concentration. So I just basically divided that over to the other side. And I could actually get a number here because I know the concentration of the bromide in this solution is 0.02 molar. That means that if I take 7.7 to the minus 13 divided by 0.02, I will get something in the ballpark of 3.9 times 10 to the minus 11 molar. So all I did is rearrange the KSP expression, solve for the silver concentration. And what this number represents is the minimum amount of silver to get the silver bromide precipitating out as a solid. So that number represents the minimum amount of silver that you have to put into that solution to start to see silver bromide starting to precipitate out. Any questions on that part of it? We could do a very similar calculation to figure out what is really the concentration of silver that's needed to start to see silver chloride come out by using the KSP expression as well. And that would be silver times chloride equals 1.6 times 10 to the minus 10. Once again, here we could solve for the silver concentration by dividing our chloride to the other side. And since we also know it's the same concentration in there, we could divide it by 0.02 molar, and we will end up with 1.6 to the minus 10 divided by 0.02 gives us something like 8 times 10 to the minus 9 molar. This number represents the minimum amount of silver needed to get silver chloride to precipitate out. So if I wanted to do this selectively, I should have a concentration of silver that is greater than 3.9 times 10 to the minus 11 molar, because when I do that, what's going to start to precipitate out? The bromide. Right. And I could gradually keep increasing the silver concentration until I actually do not see any more solid, as long as I keep it under what number? The 8 times 10 to the minus 9, which is a larger concentration. So if I keep that guy less than 8.0 times 10 to the minus 9 molar, any solid that I see come out, if I keep the concentration between those two numbers, should perhaps be silver bromide, right? And now I don't have to pick it out one by one and try to figure out which one's which. I know that it should be silver bromide. And if I was really doing this, I would continue to increase the silver concentration, keeping it less than 8 times 10 to the minus 9. And at some point, I should stop seeing precipitate, right? And that means that I have successfully precipitated out all of the bromide from that solution. At that point, if I then wanted to take the chloride out, I need to take my silver concentration and get it to 8 times 10 to the minus 9 and above, right? And at that point, I should once again start seeing solid come out. So even though we're using the same reagent to precipitate out both of those ions, by keeping the concentration under control of it, we can selectively precipitate out just the bromide first. And once we successfully get the bromide out of the way, then we can increase the silver concentration and get the chloride out of the way. And now we can actually have two separate test tubes that have silver bromide and silver chloride in it if we needed it that way. That's sort of the basis of qualitative analysis experiment. Any questions on that calculation? Could we have predicted, and why this question is written like this? Why is it written to get rid of the bromide first? I use the KSPs in this case to compare. I can't, because the top guy is 2 ions, the bottom guy is 2 ions, and we see that the larger KSP value is actually the silver chloride, right? Which means that it is more soluble, which means we expect it to stay in solution longer than the silver bromide would. So using the KSP, we can make a pretty good prediction that we should see that silver bromide precipitate out first, which is why the question is written like that, and the silver chloride would actually be more soluble. Tied it all together for you. Any questions on that there? All right, we will lay it up there. A couple of remarks.